Hello, I was presenting this work, Group Testing for Accurate and Efficient Range-Based Near-Neighbor Search for Plagiarism Detection. The authors of this work are Harsha, that's me, Kashish Mittal, and Professor Ajit Ajwade. All three of us are affiliated with Computer Science Department at Indian Institute of Technology, Bombay. Now, let's first formulate our problem. The range-based near-neighbor search problem is as follows. We are given a database of n high-dimensional vectors, say the dimensionality is D. Now, given a query vector Q in the same space, our aim is to determine all those vectors in the database D such that the similarity of the vector in database with the query is greater than a threshold row. So this is a problem, and it's required to make this algorithm efficient because it's widely used in many information retrieval systems, including search engines. There have been many existing approaches which typically convert the database of vectors into a data structure, which is often called an index, which is then later used during inference time so that the querying time is reduced. There are like KDQ methods, there are graph-based methods as well, like HNSW, there are locality-sensitive hashing-based methods, like Falcon and Falcon++, and many others. Now, many of these algorithms have particular limitations, like many of them have high index building time, which is undesirable. Many of these algorithms work only on static databases, which make them infeasible to use for streaming settings where the database is dynamic. There are too many parameters in these algorithms which are infeasible to tune for large databases. And most importantly, many of these algorithms are approximate methods. So these are unsuitable for high recall requirements, like in plagiarism detection, where missing a point can lead to unfairness. Now, our algorithm is based on the framework of group testing. The group testing was originally used in healthcare to reduce the number of tests to find the infected people in the group. Now, given a population, the population was divided into groups, and tests were conducted on the entire groups. And the individuals were tested only when a particular group was tested positive. Now, how is that related to our work? So our approach requires formulating a function h, which maps a group of vectors to a representative vector v. Now, the property of this function is that if the similarity of the vector v with query q is less than a threshold, we can be sure that none of the vectors in the group had similarity more than rho. And this helps in pruning while search. With certain assumptions on the database of vectors, we can assume them to be unit normalized and they being positive descriptors, which the softmax features are. We can construct the function h as sum of the vectors in the group. So essentially, our approach is binary splitting for group testing. How it works is, given the database, the first test is on the entire database as group, and we check the representative vector of the group with the query. And if the similarity is greater than rho, we continue the search and split the database into two roughly equal parts. Now, suppose here the group 2 here has the representative vectors similarity less than rho. So now we can be sure that none of the vectors in the group are similar to the query Q, and we can prune the search for that particular group here, and we can continue recursively the search on all those groups which are tested positive. Now, we have done experiments on 4 million scale datasets. The vectors were extracted using pre-trained regime 19 architecture, and the vectors were 1,000-dimensional softmax features, which are useful for having high recall. The coverage of our experiments is also good for algorithms. We have tested for LSH-based methods like Falcon and Falcon++, KDT-based methods like FLAN, graph-based methods like HNSW, and many other algorithms. Here are some results for a static setting. Notice that our algorithm is exact. It has perfect mean precision MP and perfect mean recall MR. And further, our algorithm beats many existing algorithms on mean query time MQT. We have also done experiments in streaming settings in which the database gets vectors added on the fly. We are not considering deletion in this work. And you can see even in this setting, the streaming setting, the index building time of our algorithm is orders of magnitude less than many existing algorithms. And also the average insertion time is orders of magnitude less than many other algorithms. We have also done theoretical analysis to bound the expected number of dot products required for a search. So assuming a sharp decay in similarity distribution of the query Q with database of vectors, we can bound the number of positive pools at each round of the test, and then sum over all those expected values to get the expected number of dot products for each search. And we found that all these datasets and many other datasets having softmax features have this property that the similarity falls off very sharply. Here are some references of our work. Okay, thank you for your time.